We start with the collected papers of Albert Einstein from 1900 to 1902, the special relativity paper. That paper was published in the Annals der Physik, or the Annals of the Physics, the volume number 17. The year is 1905. It was about 30 pages, from page 891 to 921, on the electrodynamics of moving bodies by Albert Einstein. In the introduction of the paper, it is well known that Maxwell's electrodynamics, as usually understood at present, when applied to moving bodies, leads to asymmetries. So in other way, Albert Einstein is going to deal with the asymmetries created by Maxwell's equations that relates the electrical to the magnetic properties of electromagnetism or electrodynamics. When Maxwell's electrodynamics is applied to moving bodies, it leads to asymmetries that do not seem to attach to the phenomena. Let us recall, for example, the electrodynamic interaction between a magnet and a conductor. The magnet will be, assuming you have a magnet of that form, that is the north and that is the south, and you have a conductor of that form that carries electricity. It doesn't have to be a coil. It's very simple. So you have electric current flowing this way, and you have magnetic field flowing this way. Of course, the electric current will not flow until you close the circuit. And the magnetic field, let us see now, the magnetic field will not be felt unless you bring a detector to it. So that is simply the two bodies that Einstein is going to use to explain or to discuss the issue of the asymmetry in Maxwell's wave equations. The observable phenomena depends here only on the relative motion of the conductor and the magnet. The relative motion between whether you are going to move that coil in space or you're going to move that magnet, assuming that, let us draw it again. We have a magnet, and that is the north, and that is the south pole. That magnet will have electric fields, and that electric field is only felt if you wanted to detect it. The magnet sits by itself, does not do any harm to anybody. This is the electric field line that was understood at that time. And here you have the electric wire or conductor. Assuming now we are not going to put a battery here, we are going to put some kind of galvanometer. That galvanometer has a magnet. It will only detect any current passes in that wire in any direction to be detected in the galvanometer. Here is your conductor circuit, and here is your magnet body. We are now dealing with two things: the magnet and the conductor. While according to the customary conception, the two cases in which respectively either the one or the other of the two bodies is, if the one in motion, are to be strictly differentiated from each other. What does that mean? Which means if you move one or the other, they're supposed to be differentiated, which means the effect is not the same. 4. If the magnet is in motion and the conductor is at rest, if you move this magnet, you leave the conductor at rest, there arises in the surroundings of the magnet an electric field endowed with a certain energy value that produces a current in the places where parts of the conductors are located. Another way, if you move the magnet will create current around wherever it comes close to the wire. It is not going to create the magnet everywhere around it, because the conductor is located in a certain space, in a certain location in the space. The electric current will only be generated at the coil or the conductor alone. But let us see the opposite. This is the first case, when the magnet is in motion. That is when the magnet is in motion. Can you differentiate that case from the other case? Let us see the but. If the magnet is at rest, now we are going to put the magnet at rest, and the conductor is in motion. We are going to use the wire. No electric field arises in the surrounding of the magnet, because the wire has no field. The wire is inert. The wire only gets electricity when it cuts the fields of the magnet, because the magnet a permanent magnet, but that will not be the case if the magnet is not a permanent magnet. If the magnet is electromagnet, you can make it produce field at certain location and not the other. In other way, here the magnet is active. It produces field all the time. The field is sitting there. It doesn't do any energy unless the wire cuts it. So why is Albert Einstein has a problem? No electric field arises in the surrounding of the magnet, while in the conductor an electromotive force will arise because the current is produced in it if you move the wire. To which? To that electromotive force in itself. There doesn't correspond an energy. If you have electromagnetic force, you have to have energy. How did you move the wire? You move, just moving the wire itself is an energy. Because you moved the wire, you created electromagnetic force in it. So the idea that there doesn't correspond energy, while in the conductor an electromotive force will arise, to which in itself there doesn't correspond any energy. No, it does correspond any energy, because how do you move the wire if you don't have energy? That is where Einstein gets himself in deep trouble. But which, provided that the relative motion in the two cases considered is the same. So in other way, if one time you move the magnet, it will produce current in the wire and everywhere else. But if you move the wire itself, it will only create force in the wire, but it is not going to create electric field anywhere else. But which, provided that the relative motion in the two cases considered is the same. Of course, the relative motions are not the same. They are the same in terms of their relative, but one of them is an active element and one of them is not. But which gives rise to electric currents that have the same magnitude and the same course as those produced by the electric forces in the first mentioned case. Examples of a similar kind and the failure of attempts to detect a motion of the earth. He is now going to try to figure out something else to illustrate his point. The earth is a magnet. When you move that magnet everywhere, you only detect the magnet in that wire, but you don't detect it anywhere else. If you move the wire, you get only force in the wire, but you don't get anywhere else on the surrounding. Let us now go to the earth. Of course, the failure to detect the motion of the earth, that is the Melekan experiment, when he tried to measure the difference in the speed of light in two opposite directions in relation to the earth motion, and he cannot find out a difference. Attempts to detect a motion of the earth relative to light media, that is the Melekan experiment, lead to the conjecture that not only in mechanics means the earth and the light, assuming the earth is not magnet here, assuming the earth is only the source of the light. Not only in mechanics, what he is now trying to figure out mechanics with electrodynamics, mechanics of the earth, electrodynamics of the magnet, but in electrodynamics as well. The phenomena, what phenomena? Phenomena is a relative motion. The phenomena do not have any properties corresponding to the concept of absolute rest. We are hallucinating here. What makes absolute rest jump into the situation? The earth and the light. You cannot measure the difference in the light medium even though the light is emitting from the earth. But that in all coordinate systems in which the mechanical equations are valid, also the same electrodynamic and optical laws are valid. So the validity of the mechanical equations, the Newton's equation, in all coordinate system have to be valid also in the same time when the electrodynamic and optical laws have to be valid. As has already been shown for quantities of the first order means very low speed of Earth. That's Melekan experiment, that he cannot find any difference between the direction of light in two perpendicular direction of the motion of the Earth. We shall raise this conjecture, the conjecture that the laws of mechanics and the laws of electrodynamics have to be the same in all coordinate systems, which he is going to try to make the theory of general relativity to assume that the space itself have to be curved. The curvature comes because he assumes the speed of light is constant, because the speed of light has a length and time, the length of the wavelength and the time that is related to whatever coordinate system. When you divide them on each other, he wants to curve the space. A crazy idea that will get him into a theory that nobody will ever be able to explain or utilize or exploit. We shall raise this conjecture, whose contents will be called the principle of relativity. The principle of relativity is the principle that's going to cause a lot of problems. We want us to create a system, coordinate systems, universal, where all mechanical and electrodynamic laws have to be the same, which we call it the asymmetrical in both directions. But how do you get from moving an electric conductor with a magnet into using the principle of relativity? Because the relativity here doesn't relate at all to the phenomena, because you have a big question mark that the magnet have an electric field that we don't know how it is generated in all directions. So when the magnet moves, it will create electric field in all direction, but it will only generate electric current in the wire. But when the wire moves, it will not do the same thing like the magnet, because the wire has no active field in it. The wire responds to the magnet, as the magnet does not respond to the wire. In the same of the light medium and the earth, the situation is different, whose content will be called the principle of relativity thereafter, to the status of the postulate, and shall introduce in addition the postulate only seemingly incompatible with the former one. That what is the postulate that he is going to use in relativity that's going to make everything complicated? That in empty space, light is always propagated with a definite velocity v, which is independent of the motion of the emitting body. Well, here is where things gets confusing when you assume that the light have a definite velocity. If you assume a definite velocity, you assumed already a rest place. Why would the light propagate with a definite velocity if there is no medium that is definite and at rest, which we call it the ether, which Einstein does not want it to be? But if you assume the velocity of light v is definite, and then you try to screw everything around that screwed up assumption, assuming there is no ether, there is nothing, and you are going to curve the space, that is not going to get you anywhere. Well, of course, we are assuming that the light is not dependent on the motion, on the origin of the earth. It has nothing to do with the earth, even though it is emitted from the earth, but it does not, it have a constant velocity, so it does not start from zero and speeds up. Well, that is not going to change anything. These two postulates suffice the two postulate, which is the definite velocity of the light, and other postulate, which is the independence of that velocity from the source that emitted the light. These two postulates suffice for arriving to a simple and consistent electrodynamics of moving bodies. Assuming that you cannot really get simple and consistent electrodynamics of moving bodies when all you assume is that the speed of light is constant and independent of the origin of the emitting the light, when you have here a problem that has nothing to do with the light. Well, assuming that the electromagnetic field or the magnetic field of the magnet is not independent of the source of the magnet. So when you move the magnet, well, the field have to move because the field originates, but assuming that the field is constant velocity. But here the situation is that the field propagates everywhere around the magnet because the magnet is active. You have to find out why the field originates from the magnet. So the similarity between a magnet and a conductor that have asymmetrical properties, when the magnet moves, it has effect distinctly different when the coil or the conductor moves. When the earth moves, it has distinctly different from the effect of when the light moves around the earth. The two cases, the magnet and the coil and the earth and the light, are not similar at all. If you now want us to advance the issue of relativity, how do you get the issue of relativity to explain to you the activity that one source is active and one source is receptive in the magnet and the coil, while the earth and the light are different? Let us enjoy the hallucination of our friend Einstein. Let's go to the next page. Let's first go to the second page. These two postulates suffice for arriving at a simple and consistent electrodynamic motion of moving bodies on the basis of Maxwell theory for bodies at rest. How do you arrive to the conclusion that you have simple and consistent theory when you did not start yet? Can you use Maxwell theory to deal with the issue of the Earth Melekan experiment by just assuming the light velocity is constant and independent of the source? The introduction of a light ether will prove superfluous. You already assume the constancy of the speed of light. That's exactly as assuming there is ether. Why would the light have to have constant speed if it doesn't have a constant medium? Will prove superfluous, in as much as in accordance with the concept to be developed here, the concept we are developing a concept here of relativity. But you are going to curve the entire space to make the speed of light constant. No space at absolute rest. You have no space at absolute rest, but you assumed an absolute velocity of the light. Endowed with special properties. Fine, the special properties are not our concern, but you already endowed the light. Definitive magnitude endowed with special properties will be introduced. Nor will a velocity vector be assigned to a point of empty space at which electromagnetic processes are taking place. Well, the light have to have vector. The point in space is not important, but the light have to originate from a source. If the source moves, the light have to move. So you cannot avoid having velocity vector. Like every other electromagnetics, the theory to be developed is based on the kinematics of the rigid body. The kinematics of the rigid body, which we call it the Euclidean geometry, and the x, y, z, and t, that is the kinematics. Since the assertions of each and any theory concern the relations between rigid bodies, coordinate systems, x, y, and z, clocks, t, and the electromagnetic processes, here is where you think it gets complicated. Because the rigid bodies have x, y, and z, the time is t, and the electromagnetic process which have a velocity of constant speed. Insufficient regard for this circumstance is at the root of the difficulties with which electromagnetics of moving bodies must presently grapple. What exactly is driving Einstein's mind? What is the problem that he is trying to produce? He's trying to solve a problem of the medium that carries light by getting rid of the medium and assuming a constant speed of light, and then assuming that the speed of light has nothing to do with the source of emitting light. From there he thinks he can solve the problem with asymmetry. The asymmetry means when you move one part of the two, the earth and the light, or the magnet and the conductor, in the two cases you have two things. You have rigid bodies, which is a magnet or earth, and you have electromagnetic, which is the electromagnetic field or the light. Between these two he wants to produce a principle of relativity to solve the problem of asymmetry. But the problem here is not only the origin and the speed of light and the origin and the speed of the electromagnetic fields. The problem here is not the constancy of the speed of light. The problem here is that the magnet radiates in all directions, and the earth and the light don't have the same kind of similarity, because you cannot detect the motion of the earth, or the effect of the light is not going to give you. There is no similarity between the earth and the light, the earth motion and the light, and the magnet motion and the electricity. Only, of course, the only similarity is the speed of the electromagnetic field. Other than that, the relativity doesn't work. That is the first part of the paper's introduction, or how Einstein outlines the problem he is going to tackle. Kinematic part. Definitions of simultaneity. Consider a coordinate system in which the Newtonian mechanical equations are valid. To distinguish it verbally from the coordinate systems that will be introduced later, he is going to introduce a coordinate system where all mechanical and electromagnetic equations are valid, because he does not like the Newtonian system that is sitting at rest. And to visualize it more precisely, we will designate this system as system at rest. System at rest is the system of the rigid body. If a material point is at rest relative to this coordinate system, its position relative to the latter can be determined by means of rigid measuring rods, which mean x, y, and z, using the methods of Euclidean geometry, and can be expressed in Cartesian coordinates. If we want to describe the motion of the material point have to be described. Motion means time. So you are going now to get out of the Euclidean geometry and to put time, because it is motion. We give the values of its coordinate as function of time. That is okay. How are you going to get the speed of light here to make the time different? However, we should keep in mind that for such a mathematical description to have physical meaning, we first have to clarify what is to be understood here by time. Trying here to mess with the time is not going to tackle the problems that you started with. We have to bear in mind that all our propositions involving time are always propositions about simultaneous events. If, for example, now he wants us to define time precisely. Precisely means, simultaneity means what? You have two events happening at the same time. Of course, it's impossible to determine two simultaneous things in terms of time. There is always an error. By the time you calculate one event, the other event has already been developed. Compare that error to the errors that you already are dealing with from the very beginning of the emission of light from a body, or emission of electromagnetic field from a magnet. You have enormous error here. The field emitted, how did you interact with the field? It is not only the motion of the magnet. You have an inherent error. The simultaneity is not the events only of the rigid bodies or the magnet. The simultaneity of the atomic nature of the light and the electromagnetic field and the magnetic field. If, for example, I say that, now he's going to talk about here rigid bodies. The train arrives here at 7 o'clock. That means more or less the pointing of the small handle of my clock. Of course, at that time, the clocks have handles, the small and the large, to 7. Of my clock to 7. And the arrival of the train are simultaneous. So he talked about the simultaneity of the train, the action of the train that arrived, and the pointer, the hand of the clock. They are simultaneous. Those are material bodies. So you try to calculate time based on these two material bodies. But there is another missing fact, that the bodies themselves, of course you are going to use your eyes, so you are going to look, which you have a speed of light involved here. So the speed of light have to make these two events simultaneous. What is one? We shall not discuss here the imprecision that is inherent in the concept of simultaneity of two events taking place at approximately the same location, and that also must be surmounted by abstraction. As we see that Einstein started with two problems, a magnet and a conductor, to prove that there is asymmetry when you move one object relative to the other that is different from when you move the other object relative to the former. And in the same time he tried to use the other example of the earth and the light. The two examples that he used to prove that Maxwell's theory of electrodynamics creates a problem with symmetry are not logical extension to what he is going to accomplish now. Let us see now page 142. It might seem that all difficulties involved in the definition of time, now is getting on the time, the relativity of time, where the two problems that he started with, the magnet and the coil and the conductor and the earth and the light, has nothing to do with the relativity of time. It might seem that all difficulties involved in the definition of time could be overcome by my substituting position of the small handle of my clock for time. In other way, he wants us to say that the time can be determined by the position or the place and the coordinate system, the position of the handle or the hand of the clock. Such a definition is indeed sufficient if time has to be defined exclusively by the place at which the clock is located. So the clock now is located at a place, and he is going to find the place of the small handle, but the definition becomes insufficient as soon as series of events of locations of clocks, each clock have to measure each event. Now he is going to use two clocks to measure two events and find out if he can get the location of the two clocks to define what he is going to call absolute time in terms of the absolute velocity of the light. So far he is going to define time, relative time, but would that solve the problem? As soon as the series of events occurring at different locations have to be linked temporarily, because you have two locations for events, how do you link them with the clocks? Or what amounts to the same events occurring at places remote from the clock have to be evaluated temporarily. To be sure, we could content ourselves with evaluating the time of the events by stationing an observer with a clock at the coordinate origin and having him assign the corresponding clock handle to each light signal. The light signal is what he is going to try to use the light of looking at the clock from one clock to the other to be able to connect the light to the time. In other way, he wants to make the time relative to the V, the capital V he used as the speed of light. So he wants us to make that time of measuring the events related to the time signal that attests to an event to be evaluated and reached the person who is the observer through empty space. But as we know from experience, such an assignment has the drawback that it is not independent of the position of the observer. One observer will get the signal from an event, he will get the signal from another event. We arrive at a far more practical arrangement. The new arrangement he is going to use two observers, one for each event, and one is local to each event. by the following considerations. Here is where everything is going to be started on the wrong foot. Another way, he has an event E1 here and another event E2 here. To measure the time here, he is going to put an observer O1 here and observer O2 here, and this observer will have a clock to watch this event, and this observer will have a clock to watch this event. Then he wants us to prove that you can get a time, an absolute time between these two by measuring distances, provided that he is going to use the speed of light to determine simultaneity. In other way, why would he wants to do that? He wants us to do the reciprocal or the symmetrical situation where the mechanical laws in the Newtonian coordinates will be as valid as the electrodynamic laws of the motion of bodies related to electrodynamic field, because the electrodynamic fields are propagating at the speed of light. If there is a clock at point A of a space, then an observer located at A can evaluate the time of the events in the immediate vicinity of A by finding the clock handle positions that are simultaneous with those events. If there is also a clock at the point B, we could add a clock of exactly the same constitution at that of A. Then the time of the events in the immediate vicinity of B can be likewise be evaluated by an observer located at B. So we have two observers now. But it is not possible to compare the time of an event at A with one at B without a further stipulation. What is the stipulation? The stipulation of the constant of the speed of light. Thus far we have only defined an A time at the point A and a B time, but not a time common to A and B. The time common to A and B, he wants to make the absolute time coming from the absolute velocity. The latter can now be determined by establishing by definition that the time needed for the light to travel from A to B is equal to the time it is needed to travel in the opposite direction. It is needed for the time to travel from B to A in the opposite direction. For suppose a ray of light leaves from A towards B at A time, TA, is reflected from B to A at B time, TB, and arrives back at A time at T dash A to T prime A. T prime A, which means because it started at TA and it came back, it went and it came back. The two clocks are synchronous by definition if it went to from time A, it traveled to time B, so the difference time B is longer, and it went to from time B, it came back to time A. So from this equation, he is going to find the simultaneity. By assuming that it is possible for this definition of synchronism to be free of contradictions and to be so for arbitrary points, and that the following relationships are therefore generally valid. Page 143. If the clock in B is synchronous with the clock at A, then the clock in A is synchronous with the clock in B because of the simultaneity. If the clock in A is synchronous with the clock of B as well as with the clock in C, then C is a third point, an arbitrary point. Then the clock in B and C are also synchronous relative to each other. With the help of some physical thought experiments, we have thus laid down what is to be understood by synchronous clocks at rest that are situated at different places, and have obviously obtained thereby a definition of synchronous and of time. Synchronous means all the clocks are synchronized, and the time is the time that's taken to travel between one point to another. The time of an event is the reading obtained simultaneously with the event from a clock at rest that is located at the place of the event, and that for all time determinations is is in synchrony with a specified clock at rest. Based on experience, we also postulate the quantity. Now he is going to postulate the quantity, which means the speed of light is double the speed that goes back and forth between A and B, divided by the time where the t prime is the time it took to go from A to B and come back, and the time that started from A. When you take them from each other, that will be the speed of light that defines that distance. That is a universal constant, the velocity of light in empty space. But now here you created a universal constant to define absolute or relative time. A universal constant is not explicable. You try to use something that's inexplicable to define something else that's inexplicable. It is essential that we have defined the time by means of clocks at rest. So we don't know if it's constant or not based on the first order measurement. Anyway, on the relativity of length and times. The considerations that follow are based on the principle of relativity and the principle of the constancy of the constant of the velocity of light is going to be a problem. Two principles that we define as follows. The two principles we already have defined them before. The laws governing the changes of the state of any physical system do not depend on which one of the two coordinates in uniform translational motion relative to each other these changes of the state are referred to. So in other way, this is the Newton's first law of motion, which means a uniform motion in a straight line. The laws that governing that change do not depend on the coordinate system. Each ray of light moves in the coordinate system at rest with a definite velocity v, independent of whether this ray of light is emitted by the body at rest or a body in motion. In other way, he wants us to say the speed of light is constant, independent of the body that emits it. Assuming there's two postulates of relativity, of course they have to be valid, except the velocity of the light. How would that going to solve the problem of magnet and the coil and the earth and the motion of the motion of the light? On page 144, here's where things will go wrong for Einstein. The velocity of light, where he assumed have to be constant, equal to the path the light took. In this case, he defines the path in an awkward way between event A and event B. He defined that the time path, you go from A to B, assuming you started here at time t, and you arrived here at time tb. When then you came back to define simultaneity, he wants to prove that the time have to be equal both ways. When you return back from tb to time here will be t prime a. So he defines that distance, that he calls that distance r, or a distance AB. Then he is going to assume that there are two situations, that the measuring rod that measuring the distance between A and B is moving along the light with a speed of v. So if you measure it in this direction where the light is moving with the capital V, in that direction the rod will be moving with V minus V. When you return, it will be V plus V. So in this case, he wants us to prove that two things. You are measuring the distance between A and B. A is an event, B is another event. The time is determined by the velocity of traveling that determines simultaneity, and the length, the light length, and the time traveled. Where time travel, the time interval. Where time interval would be understood in the sense of the definition of section 1. We already have section 1 before that determine the time definition, the interval. What does section 1 look like? If you go back here, that is the definition of simultaneity, or the time interval from T prime to coming back to TA, cutting the distance of 2AB, going and coming back. Let there be a given rigid rod at rest. That rigid rod, he is going to use that rigid rod to measure the distance. Its length measured by a measuring rod that is also at rest shall be L. So L is the distance that you are going to use, a unit of the distance to measure the distance between A and B. We now imagine that the axis of the rod is placed along the x-axis of the coordinate system at rest, and that the rod is then set in uniform parallel translation, which means moving in a straight line at uniform speed, called V. Remember, here is a special relativity, is going to use uniform translation. In the general relativity, is going to use acceleration. In either case, you are going to have a problem, because the causation of the theory, the main causation, is missing. The causation is that he assumed a universal constant called V, speed of light. That causation cannot make the entire theory function in the direction he wants it to be. So you are measuring by a rod in a uniform parallel velocity translation V along the axis x. X is the distance from A to B in the direction of increasing x. We now seek to determine the length of the moving rod, the length which is the distance from A to B, which we imagine to be obtained by the following two operations. So observer co-moves with the above mentioned measuring rod. One observer is sitting on the rod and moves with it. That is the observer at rest, and the rod to be measured, and measures the length of the rod directly by applying the measuring rod exactly as if the rod is to be measured. The observer and the measuring rod are at rest. That is the first observer sitting on the rod. That's measuring the distance. Using the clock at rest that are set up in the system at rest, and that is the person at rest at the rod, and are synchronous in the sense of A. Section A is what we have just mentioned before. The observer determines the points of the system at rest at which the beginning and the end of the rod to be measured are found at some given time t. The distance between these 2 points measured by the rod used before, which in the present case is at rest, is also a length which can be designated as the length of the rod. That is number B. So you are measuring those one observer sitting on the rod, measuring it while it goes. The other observer is sitting on the fixed frame where the other clock is. According to the principle of relativity, the length to be found in operation A, which we shall call the length of the rod in the moving system, this is a moving system, must equal to the length L of the rod at rest, because you have 2 measurements now. One person sitting on the rod and measuring as it goes, and one person is sitting on the fixed frame, the other frame that's not moving, and each one of them has a length, and these lengths have to be equal. We will determine the length to be found in operation B. Operation B is using the clock at rest, which is not moving, that are set up in the system at rest and are synchronous in the sense of P, which we shall call the length of the moving rod in the system at rest. So we have now 2 systems of measurement. The moving measurement is the length of the rod while moving, and measure it while at rest. Why is he measuring the length of the rod? Because he wants to find a connection between the distance between the 2 clocks and the timing of the two clocks, and he wants to link that to the speed of light on the basis of the two principles, and we'll find it to be different from L. Why it is different from L? Because there is a relative speed. The commonly used kinematics tacitly assume that the lengths determined by the two methods are exactly identical. You might say, well, what is this guy talking about? The distances are very small if you are dealing with the Earth and the light. The light have enormous speed, while you are measuring with very simple equipments, or the magnet and the conductor. The difference between the length when you measure it, by the time you go from one end to another, is not going to be very considerable difference in length. Or in other words, that in the time epoch t, a moving rigid body is totally replaceable as far as geometry is concerned by the same body when it is at rest in the particular position. Further, we imagine that the two ends A and B of the rod are equipped with clocks that are synchronous with the clocks of the system at rest, i.e. those readings always correspond to the time of the system at rest. He wants us to make sure that the time of the system at rest is not the time of the system that is moving. Of course they are not, because there is a velocity, there is a relative velocity at the locations they happen to occupy. Hence, these clocks are synchronous in the system at rest. We further imagine that each clock has an observer co-moving with it, and that these observers apply to the two clocks the criteria of synchronism formulated in section 1. Suppose a ray of light starts out from A at time t, is reflected from B at time tb, and arrives back to A at time t prime A, taking into account the principle of constancy of the speed. This is the theory of Lorentz transformation. When the light traveled from A to B, it arrived late at TB, and the distance was the velocity minus the speed of the rod, and that's the distance RB is the distance between A and B. But when the light returned from TB to the original point, it arrived at later time, but the velocity was different. Well, this is the experiment of Melekan experiment, where RB denotes the length of the moving rod measured in the system of the at rest. The observers moving with the moving rod would thus find that the two clocks do not run synchronously, while the observers in the system at rest declare that them synchronous. Well, here you have a problem. You either have to find out that the two clocks are not synchronized because of the difference in the change in the direction of the speed, or the two rods are different in length because the measurement of the length was done at different velocities. Here is the most ridiculous idea, with that you assume that the simultaneity of measuring a rod on Earth or in a laboratory will make that much difference in the definition of time of measurement. We already have enormous error in other variables of any experiment. That's what makes the theory of relativity a bogus assumption. Thus we see that we must not ascribe absolute meaning to the concept of simultaneity. Instead, two events that are simultaneous and when observed from some particular coordinate system can no longer be considered simultaneous when observed from a system that is moving relative to the, of course we know that for sure. So that is not a discovery that you are assuming that because the system is moving, one part of the system is going to see it at different velocity from the other, so they are not simultaneous. So what discovery is that? There is not much there. Number 3, section 3. Theory of transformation of coordinates and time from a system at rest to a system in uniform translational motion to it and time. This is the Lorentz transformation. Let there be a given two-coordinate system in the space at rest, i.e., two systems of three mutually perpendicular rigid material lines issuing from one point. Let the x-axis of the two systems coincide, and their y and z-axis parallel. Each system shall be supplied with a rigid measuring rod and a number of clocks, and the two measuring rods and all the clocks of the system should be exactly alike. Time here means both time of the system at rest and the position of the hands of the moving clock located at the same place in question. So now this experiment, the same experiment, but he makes in 3 dimensions. You have a system that's x, y, and z. That will coincide with another system. That system will be x prime or x2, and that will be y prime or y2, and that is z, and that's y. The relative motion will be in that direction. That is the velocity v. So y is not going to be affected, z is not going to be affected, only x will be affected. The origin of one of the two systems k shall now be imparted a constant velocity v in the direction of increasing x of the other system capital K. So one of these systems is capital K and the other system is small k, and that's the velocity v, which is at rest. And this velocity shall be imparted to the coordinate axis. The corresponding measuring rod and the clocks are also imparted with that velocity. To each time t of the system at rest capital K, there corresponds then a definite position of the axis of the moving system. And for reasons of symmetry, we may rightfully assume that the motion of k, small k, can be such that the time t, small t, t always denotes a time of the system at rest, and the axes of the moving system are parallel to the axis of the system at rest. We now imagine the space to be measured both from the system at rest capital K by means of the measuring rod at rest, and from the moving system small k by means of the measuring rods moving along with it, and that the other coordinates are obtained in this way. Further, by means of the clock at rest in the system at rest, and using light signal in the manner described in section 1, the time t at rest of the system at rest is determined for all its points where there is a clock. Likewise, the time tau of the moving system is determined for all the points of the moving system having clocks that are at rest, relative to, relative to this system. So we have two systems, two clocks, two measuring rods, and we try to figure out how to relate the time measured in a moving system to the time of the system at rest. Applying the method of light signal described in section 1 between the points containing these clocks. To every system of the values x, y, z, and t, this is a constant that determines completely the place and the time of an event in the system at rest. There corresponds a system of the Latin corresponding that fixes these events relative to the system small k, the moving system. And the problem to be solved is to find the system of equation connecting these two quantities. We already did that, but he is going to make it in 3 directions just to make life miserable a little bit. So that system is a moving system, and that is a system at rest. First of all, it is clear that this equation must be linear because of the properties of homogeneity that attributed to space and time. Assuming a linear because he have a uniform velocity and moving in one direction. There is a homogeneity to space and time. Why did he assume there is a homogeneity? Because he likes it. If we put x prime equal x minus vt, x is at rest, vt because of the speed, then it's clear that the point at rest in the system K, that's the moving system, has a definite time-dependent system of coordinates x prime, x, y, and z, which because only x will change, because only x will move in that direction, and the y and the z are the same, belonging to it. We first determine tau as a function of x prime, y, and z, and the t. Tau is the time in the moving system, and the x prime was already being defined by that linear motion. To this end, we must express the equation that tau is, in fact, the aggregate of readings of the clocks at rest in the system K, which has been synchronized according to the rule given in section 1. Suppose that at time tau 0, a light ray is sent from the origin of the moving system K along the x-axis to x1. x1 is on the moving place, and it is reflected from there at time, after it got there, at time tau 1 towards the origin. When it arrives at time tau 2, we then must have, this is the same definition of the simultaneity of time. So because the signal went back and forth, it started at tau 1, it went to tau 2, it came back to tau 3. If you divide it by half, you get the absolute or the relative time in the frame B. Or if we write out the arguments of the function tau and apply the principle of constant velocity of the speed of light at rest, you are going to have, that is the time in the rest place. You're going in one direction, you're coming back in the opposite direction to the point, and this is a coordinate system. That is the time, and this is x, y, and z, that the initial, this is the tau at the moving system, referred to, as you see, this is a four-dimensional Cartesian coordinate. This is the tau at x0, y0, z0, and t, and this is the tau at x0, y0, x, y, and z, and the different time here because it went and came back, and he took the half. In other way, he just substituted that tau is that portion, and the tau t is that portion, and the tau 1 is that portion. From this we get if x prime is chosen infinitesimally small. So he gets a partial differential equation that change the relative change of tau in the moving to the rest depends on the difference of velocities. When you're going from going in one direction and returning in the opposite direction, you subtract the velocities. The rate of change of tau with respect to t, or the moving frame with respect to the rest frame, depend on the velocity of motion and the two directions, and that is the average, will equal to the change of tau divided by the velocity multiplied by the t, that is the distance, and that x prime is the distance in the moving frame. The change of tau will equal to the change of tau with respect to the initial time minus multiplied by the difference in velocity, or that equation will equal to 0. It should be noted that instead of the coordinate origin, we could have chosen any other point at the starting point of the light ray, and the equation just derived therefore holds for all values of x, y, and z. Analogous reasoning applied to the h and z axes, y and z axes yields. If we consider that the light always propagates along these axes with the velocity square root v square minus capital V square minus v, we observe when observed from the system at rest. Another way, the relative time difference in the moving frame is 0, that there is no change in y because they are parallel. This equation yields since tau is a linear function, that tau is the time in the moving frame is almost a constant, some constant, time in the rest frame minus a factor dependent multiplied by the change in, where a is a function of phi v as yet unknown, another unknown, some unknown. We assume for brevity that the origin of the frame k. We have t equals 0 and the tau equals 0. So now he inserted another function to determine the difference between measurements, the simultaneity of one frame to another frame, assuming that one frame is moving at its velocity v and the constant of light is capital V. Before we move anywhere from here, you can tell now there is a definite problem with relativity, is that you made a very false assumption. The speed of light is constant. The speed of light is length divided by time. You assume that's constant. What makes the speed of light is constant? That is a ridiculous assumption, and on that ridiculous assumption you use it as a causation to build a theory that gets you nowhere. Using this result, we can easily determine the quantities, the coordinates of the moving frame, eta, zeta, and whatever this function in Latin, x, y, and z in the moving frame. For a light ray emitted at time tau equals 0 in the direction of increasing the coordinate x, we will have the coordinate x, the velocity of light assumed constant, and the time in the moving frame tau. Or he is going to use tau from the previous equation and use the original time at rest with the relative velocity between the two frames, with the distance x in that measured from rest with some constant a, but as measured in a system at rest. Why did he measure at the system at rest? Because he used the time at rest. He used the distance at rest. He used the relative speed between the two frames to measure the distance in that frame, in the moving frame. The light ray propagates with velocity capital V minus V relative to the origin of k. There is a contradiction. Why would you assume that the light ray propagates with velocity capital V minus V? You assume the light velocity have to propagate only with the velocity of V. It should not be relative to that frame. So that the time t, the absolute time t, equals the time measured in that x divided by V minus capital V minus V. So in other way here, he contradicted himself by saying the light ray propagates with the velocity V minus V relative to the origin of k. Substituting this value of t in the equation for this value in that equation, we obtain the distance x in the moving frame, that's x measured in the rest frame, that's the velocity of relative between the two frames, that's the speed of light, and that's the constant a that is unknown. He is going to determine it in a minute. And analogously, by considering light rays moving along the two other axes, he was able to get the perpendicular distance eta and the other perpendicular distance to have a constant multiplied by the original distance, assuming that, of course, if v is very small, that will cancel, that will be 1 equal, will be eta will be y and zeta will be z. If we substitute for x prime its value, we obtain the perpendicular axis is supposed to be equal to the perpendicular axis at rest. Analogous reasoning apply to the h and z axis, or you can say y and z axis yields. If we consider that light always propagates along this axis with the velocity, so he assumed that light propagates along this axis with the velocity v squared minus v when observed from a system at rest. Let us try to make a reason of that. Now we have a system at rest here. That is y, that is z, and that is x. And you are traveling with another system that is eta, that is eta, and that is zeta. And you're traveling here with a velocity v, and that is k, small k, and that is capital K. He assumes that if that frame travels in this direction v, and that light travel in this direction capital V, he made a bizarre assumption that light will travel in this direction, square root of v square minus v square. Where did he get that from? This is small v. He got that from assuming that is, are you measuring this light from in this direction? If you assume that this light is small v and this light is capital V, so he assumes that the light will travel in this direction from Pythagorean theory from v square minus v square. Very bizarre idea, very bizarre idea. This is where the fabrication starts. So now we have that great fabrication, that's a perpendicular velocity, the perpendicular measurement, this is a moving frame, assuming the light moves in the z direction by v square minus v and the other direction by v square. There is no justification whatsoever for this fabrication. Before we leave this page, that is page 148, the three main conclusions of these sections is that the distance in the direction of x, the distance in the direction of y, and the distance in the direction of z between the moving bodies, this is the moving bodies on this side, and the body at rest, this is the body at rest, assuming this is the direction of z and that's the direction of y and that is z. To summarize, in the direction of x prime, and that is the distance measured in the moving frame, you have a factor here with an unknown constant a and the relative velocity small v relative to the speed of light capital V. In the direction of y, you don't have that constant, you have only that term capital V and small v. In the direction of z, you also have the same term. We're now at page 149, that is the main conclusion of the previous section. He was able to define the time in the moving frame, tau, the distance in the moving frame in the direction of x, the distance in the moving frame in the direction of y, the distance in the moving frame in the direction of z. Then he was able to reduce things to a function called the phi function of z. That is where things become making a business out of nothing, and the constant of beta that he is going to define it as this constant beta is 1 over the square root of the 1 minus the relative velocity of if the velocity is very small, beta is equal 1. Velocity is very small means if your measurement, if the speed of the moving parts are very small compared to the speed of light, which is usually the condition in life, beta is equal to 1. And phi is a function of v that is yet unknown. How did you get yourself in such trouble by having an unknown phi, When you already assumed an unknown constant speed of light, you don't know why it is constant. If no assumptions are made regarding the initial position of the moving system and the 0 point of tau, then an additive constant must be attached to the right hand side of these equations to account for where is the 0. Now we have to prove that every light ray measured in the moving system propagates with the velocity of v. If it does so, as we have measured in the system at rest, for we have not yet provided the proof that the principle of the constant of the speed of light is compatible with the relativity principle. Another way he is going now to try to prove that the constancy of the speed of light can determine the function phi. Suppose that at a time t equal tau equals 0, when the two frames are at rest, a spherical wave is emitted from the coordinate system, which is at that time common to the two systems, and that this wave propagates in the system k, which is rest, with a velocity capital V. Then if x, y, and z of that frame is a point just reached by this wave, we will have the radius from the origin, which is the square of the radius, x squared plus y squared plus z squared, equals the square of the time and times the square of the velocity. Because if it's a spherical wave, we transform this equation using our coordinate transformation equation, and after a simple calculation, which of course we have this is the fixed frame and this is the moving frame. We already have this relationship from the top before. If you look at the top equation, we already have this equation right here. Thus the wave under consideration is a spherical wave of propagation velocity v, also when it is observed in the moving frame. This proves that our two fundamental principles are compatible. The transformation equation we have derived also contained an unknown function phi of v, which we now wish to determine. He is going to determine phi. To this end, we introduce a third coordinate system k prime, capital K prime, which relative to the system small k is in the parallel translational motion parallel to the axis, such that its origin moves along the axis with the velocity minus v. Let all three coordinates origins coincide at time t, and let the time t prime of the system k prime be 0. K prime means a retreating system. At time equals 0, t, x, y, z equals 0. We denote the coordinate measured in the system k prime by x prime, y prime, z prime, and by twofold the multiplication of our transformations. The twofold is because of going and coming back. In the retreating system, the prime system, he substituted the velocity by minus v. Every velocity will be minus v, and you added to the t another term because of the velocity, and you came up with this transformation for the retreating frame. Another way, you have three frames. The frame of k, that is at rest. Relative to that frame, the frame of small k, of course at this frame, this is the x, y, and z coordinates, and this frame is x or theta of eta and z, and this frame is going in this direction with the velocity of v. Now he invented a third frame k, call it k prime, moving in that direction minus v. That is to prove the simultaneity in the 3 dimension. Since the relationship between x prime, y prime, z prime, and x, y, and z do not contain the time t, the system k and k primes are at rest relative to each other because one of them is going in the opposite direction. because k prime is going to the opposite direction of small k. It has to be at rest with respect to t. He just proved the same equation of Lorentz transformation by just replacing the velocity by minus v to get the opposite, the retreating frame, assuming that you are on the moving frame and putting a third frame, in order to prove that the function, the product of phi for v equal phi minus v. That is the exact equation driven by Lorentz transformation for two opposing, for a beam going and returning back, to prove that the two frames of references should not change the laws of physics. Since the relations between x prime, y prime, z prime, and x, y, and z do not contain the time t, the system k and k prime are at rest to each other, and it is clear that the transformation from k to k prime must be the identity transformation. Hence, the identity means the similarity. These two, the product of these two have to be equal to 1. That was proven before by Lorentz transformation. Let us now explore the meaning of phi v. We shall focus on that portion of the h-axis of the system k that lies between zeta or kappa, eta, and kappa equals 0, or the initial point, and the same situation where eta equal L. This portion of the x-axis is a rod that moves perpendicular to its axis with velocity v relative to the system k, and those ends possess in k the coordinates. That is a rod that has L, eta equal L perpendicular, and it moves with the velocity v, perpendicular to the axis with velocity v, relative to the system k, which is at rest, and those ends possess in k the coordinates. The k is the rest coordinates. These are the coordinates of the rod. It moves in that direction vt, it moves in that direction L, which is a perpendicular, divided by phi, in that direction at z. That is one point. There's 2 points on that rod, and the other point is v, and the y is 0 because on the x-axis, and that is z. The length of the rod, that length is L, measured in k, is thus L divided by phi. This establishes the meaning of the function L. He wants us to say the function L will transform the distances. For reasons of symmetry, it is obvious that the length of the rod measured in the system at rest and moving perpendicular to its own axis can depend only on its velocity and not on the direction and the sense of its motion. Thus, the length of the moving rod measured in the system at rest does not change when v is replaced by minus v. From this we arrive that the length, whether at v or v minus v, have to be equal, and therefore phi and minus phi is equal. Well, that assumption was already, that's the Lorentz transformation. It follows from this relation and the one found before that phi must be equal to 1, so that the transformation equation obtained becomes, so now he concluded that phi equal to 1 to make it symmetrical or identical. Those are the transformation, the Lorentz transformation that he obtained between the moving and the rest, only depending on the velocity, where the beta, that is the Lorentz transformation constant, only applied in the direction of x. The y and the z are independent of the transformation. So what is new here? Nothing new. We already got the same conclusion that's obtained by Lorentz transformation. Number 4, section 4. The physical meaning of the equations obtained concerning moving rigid bodies and moving cracks. What are the meaning of this? He wants us to figure out, to convince you, or to get a meaning of these equations. We consider a rigid sphere of radius r that is at rest relative to the moving system small k. and this center lies at the origin of K. The equation of the surface of this sphere which moves with velocity v relative to the system K, small k, is that sphere, i.e. a body possessing a shape of a sphere when investigated at rest. In the moving frame, a sphere in the moving frame has coordinates psi or eta or zeta squared equals the radius of the sphere, because zeta is going to be dependent on the speed of the frame. Is going to replace zeta by that term that came from the relativity to prove that the sphere is going to be converted into an ellipse. Looks like a very neat assumption or mathematical derivation, but it has a very odd assumption that make everything doesn't make sense. You assume the speed of light is a constant, and you went crazy about the mathematics to prove stuff that don't even exist. Expressed in x, y, and z, the equation of this surface at the time t equals 0, which is absolute time in the rest frame at t equals 0, is going to replace those terms from the previous equation. He is going to use the three coordinates transformed between the rest frame on this side and the moving frame on this side, with the constant beta brought from Lorentz transformation, to prove that a sphere, you don't have to prove, you are not proving any science when you prove the sphere is going to be an ellipse. That is the new ellipse, the shape of the sphere in the moving frame, and the ellipse is created by the relative velocity of the frame to the speed of light. A rigid body that has a spherical shape when measured in a state of rest, thus in the state of motion observed from a system at rest, has the shape of an ellipsoid revolution with the axis of revolution. How would that do any good? It will not do any good whatsoever. Thus, y and z dimensions of the sphere, and hence also of every rigid body, whatever its shape, do not appear to be altered by motion. The dimensions in the x, y, and z do not appear to be altered by motion. The x dimension appear to be contracted by a ratio. That contraction, of course, it is not a physical contraction. It's contraction in the measurement, i.e. the greater the value of v, the greater the contraction. At v equal capital V, that term will be equal 0. All moving objects observed from the system at rest shrink into a plane structures. For superluminal velocities, our consideration become meaningless. We shall see in the consideration that follow that in our theory, the velocity of light physically plays the part of infinitely great velocities. It is clear that the same results apply for bodies at rest in a system at rest that are observed from uniformly moving system. We further imagine that one of the clocks that is able to indicate time t when at rest relative to the system at rest, and the time tau when at rest relative to the system in motion, is replaced in the origin of small k and set such that it indicates the time tau. What is the rate of this clock when observed from the system at rest? He wants us to measure the rate of time flow in the moving frame when it is seen in the rest frame. The quantities x, t, and tau, which refer to the position of this clock, are obviously related to the equation that is the tau, that the time tau in terms of the v and x and t and y. Of course, if v equal to 0, that term will disappear, that time will equal to that time. The time measured in the rest at rest will equal to the time measured at motion. Problem here, why are you worried about the time and the frame at motion? X equal Vt, that is the motion, the distance of the moving frame at speed equal V times t. Thus we have the time tau of the moving frame equal to the time in the rest frame minus, of course he expanded that the square root by the binomial theorem, assuming this number is very small, and he obtained that number, and the t will disappear with that t, and you are going to have square root of 1 minus v square over capital V square multiplied by t. That's the time of the moving frame compared to the time at rest, because this amount is less than 1, which means the time at the moving frame will shrink, which shows that the clock observed in the system at rest is retarded each second by 1 minus that the root square second, or with quantities of the fourth and the higher order neglected by almost, if you neglect the higher orders, by half, because you are going to bring that half down, v over v square seconds. This yields the following peculiar consequences. Of course, a lot of things that's done by Einstein have to be peculiar. This yields the following peculiar consequence. If at a point A and B of capital K, there are located clocks at rest, which, observed in a system at rest, are synchronized, and if the clock in A is transported to B along the connecting line with velocity v, well, how are you going to connect to move it at velocity v from A to B? Then upon arrival of the clocks at B, of course when they arrive at B there is a velocity. What is going to make things change? How would that benefit you? The two clocks will no longer be synchronized. Well, most bizarre, peculiar logic of Einstein. Why would you worry about the synchronization of the two clocks when you already moved them from one place to another at a velocity of p? Instead, the clock that has been transported from A to B will lag f times t v square divided by v square, up to quantities of the fourth and the higher orders behind the clock that has been in B from the outset, if t is the time needed by the clock to travel from A to B. Of course, there is no lagging, there is nothing going to change whatsoever. The lagging here is because you are putting things in motion, so you are assuming there is lagging, but you have a motion. So the clock are not going to change and the time is not going to change. We see at once that the result holds even when the clock moves from A to B along an arbitrary polygonal line, and even when the point A and B coincide. If we assume that the result is proved by a polygonal line holds also for a continuously curved line, then we arrive at the following proposition. If there are two synchronous clocks in A, and one of them is moved along a closed curve with constant velocity until it has been returned to A, which takes, say, t seconds, then this clock will lag on its arrival to A, will lag behind the clock that has not been moved. From this we conclude that a balance wheel clock that is located at Earth's equator must be very slightly slower than an absolutely identical clock subjected to otherwise identical condition that is located at one of the Earth's poles. And here, from here, you can tell the man is a crook. So you started with the theory and you screwed up. From this we conclude, look at the most bizarre screwed up logic. From this we conclude that a balance wheel clock, suppose a clock that's not wheels, a digital clock, because we are only measuring the time, that is located at the Earth's equator, must be, because the Earth's equator moves at very fast, about 1,000 miles per hour, must be very slightly slower, that clock will be slower, than an absolutely identical clock subjected to otherwise identical condition that is located at the Earth's pole, because the Earth's pole has zero velocity. So that maniac assumes that the two clocks, that has nothing to do with simultaneity. Here he started with simultaneity of two things related to each other and he forgot. Here you have a clock at the pole, the Earth's pole, and a clock at the equator. He thinks those two clocks will lag, or one of them will be slower because one of them is moving fast, but this motion has nothing to do with the motion of the ball. From here you can tell they cannot trust Einstein for doing any science. The addition theorem of velocities. In the system K, small k, moving with velocity v along the x-axis of the system capital K, let there be a point moving according to the equation. That is the addition theorem of velocity. He is going to add velocities according to make an algebra of velocity. In the moving frame, the distance is xi with some velocity in that direction multiplied by tau, the time in the moving frame. Eta in the perpendicular to xi, another velocity in that time frame. And this, he have only two directions now. He assumed theta is 0, where wc and the w eta denote constant velocities. We check the motion of the point relative to the system K. K is this is the rest frame and this is the moving frame. So we seek the motion of the point relative to the system K, introducing the quantities x, y, and z and t of those are the rest frame into the equation of motion of the point by means of the transformation equation derived in the previous section. So you are going now to transform these equations xi, eta, and zeta in terms of the x, y, and z with the velocities that you put in that moving frame. Thus, according to our theory, the law of parallelogram of velocities hold only in the first approximation, but parallelogram means the Pythagorean addition of velocities. That law of the law of parallelogram of velocities. Parallelogram, which means if you have a velocity in that direction, say v1. Let us call it, if you have a velocity in that direction, say this is the velocity in the direction of eta, and you have a velocity perpendicular to it, say this is the velocity in the direction of another velocity. So the parallelogram means you draw a parallel from here, and you draw a parallel from here. This is parallel to this, and this is parallel to this, and then you draw this is your resultant. This is the law of velocities. He said that law of parallelogram of velocities hold only to the first approximation. Why it holds for the first approximation? Because you are not going, as you can tell here, this is not linear. We put a certain speed, that is the speed in the x and y in the station in the rest frame, and that is the speed in that is the moving frame. That is the diagonal speed. That's the Pythagorean speed in the rest frame. That's the Pythagorean speed in the moving frame. and that is the angle. This is arc tangential, or the reverse of the tan. You can call this the tan of that nature minus 1, the reverse of the tan of the angle between the two velocities. Alpha should be considered as the angle between the velocities v and omega after a simple calculation we obtain. He wants to prove that. He wants to prove what? That velocity, when you substitute by dx by dy, and you square it, and that is the square root when you after you put the substitution. That is the velocity measured in the rest frame of the velocities in the moving frame. It was noteworthy that V and W, V is the velocity that corresponds to, V and W are the velocities in the rest frame that corresponds to eta and theta in the moving frame. It is noteworthy that V and W enter the expression for the resultant velocity. The resultant velocity is this velocity, the diagonal velocity, this one right here. In a symmetrical fashion, if W2 has the direction of the x-axis, we obtain that the velocity equal V plus W over the term. It follows from this equation that the composition of two velocities are smaller. The composition of two velocities are smaller than V always. It follows from the equation that the composition of two velocities that are smaller than V, the composition, which means the product, always results in a velocity that is smaller than V, because you have to multiply it by this. You have to have this term in the denominator. For if we put V equal capital V minus K and the W equal capital V minus lambda, where K and lambda are positive and smaller than V, we get he is doing a lot of calculation that get you nowhere. He wants us to prove the velocity, no matter what, it is going to be smaller than the speed of light. It follows further that the velocity of light V cannot be changed by compounding it with a subluminal velocity. For this reason, we get the velocity of U equal the velocity of light plus some constant divided by that constant. For the case that V and W have the same direction, the formula for U could also have been obtained by compounding the two transformations according to section 3. For the case that V and W, V is the velocity along the x-axis, W is the velocity along the y-axis, that is in the rest frame, corresponding to those in the moving frame, have the same directions. For the case that W and V have the same directions, the formula for U could also have been obtained by compounding two transformations according to section 3. If in addition to the systems K and capital K and small k, which figure in section 3, we also introduce a third coordinate K prime, which moves parallel to K and whose origin moves with the velocity W along the axis, some axis. We obtain relations between the quantities x, y, z, and t and the corresponding quantities K prime that differ from those found in section 3 only insofar as V is being replaced by the quantity by that quantity. From this, we see that such parallel transformations form a group, as they indeed must. We have now derived the required proposition of the kinematics that corresponds to our two principles, and will now proceed to show their application in electrodynamics. Part 2. electrodynamics part. Section 6, transformation of the Maxwell-Hertz equations for empty space on the nature of electromotive forces that arise upon motion in a magnetic field. Let the Maxwell-Hertz equation for empty space be valid for the system at rest capital K, so that these are the Maxwell-Hertz equations where x, n, m, x, we know what x, y, 1 over v1 over the speed of light, the rate of change of xt, the rate of change of y, the rate of change of z, equal some differentials, two differentials. That looks like a vortex, or a curl, because you see x here, then y and z. X here is y and d. X, z here is x and y. So that is a vortex. And then when you reverse, or a curl equation, when you reverse the equation, that is x, y and z. That is y, z and x. That is z, x and y. Which means you have a curl equation, where x, y and z denotes the vector of electric force, and L, M, N that of magnetic force. So the magnetic force, the field is B, that is the magnetic force, and that is the electric force of E. The electric force, the vector of the electric force E, and those are the vector of the magnetic force P. That is the Maxwell-Hertz equation. If we apply the transformation derived in section 3 to those equations, in that we refer the electromagnetic process to the coordinate system introduced there, which moves with the velocity v, we obtain the following equation. He is going to get a parallel equation by transforming Maxwell-Hertz equations. In section 2, the electrodynamic part, transformation of Maxwell-Hertz equation for empty space and the nature of the electromotive force that arise upon motion in a magnetic field. As we have seen, Einstein capitalized completely on a simple assumption that the velocity of light is constant and there is a relative velocity of two frames. The problem is that he gets himself in trouble when he forgets the configuration that the two frames have to start from the same point, and the simultaneity is measured only by measuring the time between 2 points in the two frames that are moving relative to each other. The problem when he forgets this assumption and to try to generalize it on something that is completely different, like the motion of the Earth at the equator and the motion at the poles of the Earth. Putting a clock at the equator and to try to compare the time between the equator clocking rate or the rate of time flow at the equator to the rate of time flow at the poles of the Earth is completely bogus, because the two frames did not move with respect to each other. They did not start from one point and depart away from each other. There is no sense to apply the Lorentz transformation between the equator and the North Pole, because one of them has a different velocity from the other. You are supposed to have one of them is moving away from each other at that velocity. Let us now see how Einstein is going to introduce his screwed up theory of relativity that does not have causation other than the speed of light is constant. When we come to the Maxwell-Lorentz equation, the first equation is the relationship between the time derivative of the electric field. Look at this equation on that side, partial derivative of the electric field E with respect to the time t multiplied by the permittivity and electric constant. That's on this side. On the other side of the equation, that is the curl of the magnetic field B. This is the two sets of the equation of the electric and the magnetic field. On this side, you can look at this equation right here. On this side, the curl of E equals the time derivative of P, that is this side of the equation, and that is this side of the equation. Now when you replace where X, Y, and Z, those are the electric components, and those are the magnetic components of the magnetic field. If you apply the transformation derivatives of section 3 to those equations, in that we refer the electromagnetic processes to the coordinate system introduced there, which moves with velocity v, we obtain the following equations. Another way wants to transform the Maxwell equations from x, y, and z, from the coordinates x, y, and z, and t, that is the frame at rest, to the moving frame. X will become, and that is eta, and that is zeta, and that is tau. That is the moving frame. Of course, here the reason you have a derivative with respect to t is because you have a conductor moving at a certain velocity with respect to a magnet. So that time t here is the rate of change of a conductor. Let us see what does a conductor look like. Let us first take a simple example of a coil. That is a conductor that's connected, that has some sort of a galvanometer. And inside that conductor we are going to use a magnet. That is a magnet. And that's the conductor. So the relative velocity between the magnet and the conductor is going to create the time of change t. So what is the problem that Einstein tried to solve? He is trying to solve a problem that has no existence in reality. Assuming that you have an electron moving in that coil, that electron is going to move with the velocity v. So that v has nothing to do with the other. That is the velocity of the electron v. So in the frame, that is the rest frame. The rest frame, we call it K. That is the frame where the magnetic and the electric fields are being used. That is our frame. The frame that is on the electron, we call it small k. That's frame that is moving with the electron at a velocity of v. He is going to transform x, y, and z, the electric component and the magnetic component, from the frame k, the rest frame, to the frame small k on the electron that is moving inside the coil or the wire. The coordinates on the electron are the tau, the eta, and the zeta, and the sigma, corresponding to x, y, and z, and t. And that the velocity here will be the velocity of the electron inside the wire compared to the velocity of light inside the wire. Most of the time, the electron moves very close to the speed of light. So that factor is almost 1. Does that make any difference? But the problem here is that do you really need to factor the electron speed inside the coil and transform your electric and magnetic field from a rest frame K to the moving frame of the electron. What was that produce? The problem here is the mathematics are simple, but the reasoning might not be that simple, because you simply, of course, the electron have to be moving at the speed of light, or close to the speed of light inside the wire. So that is going to create a problem in terms of, are we really dealing with a real problem or a completely hypothetical problem? As you can tell that Einstein or transformed in his own head the components of electric and magnetic field from K frame, and the K frame, that is a rest frame. He moved it to the K frame, the small K frame that is moving with the electron, that is moving, and that is rest. Here you have the L, you have the M, those are the magnetic, and you have the N. And the electric, here you have the X, you have the Y, and you have the Z. Those are what we measure in our frame or laboratory. He is going to transform them into that frame. This frame is moving the velocity V, that is the electron motion inside the coil. How is he going to transform this component to this component? The M component is transformed to M plus small v over capital V or C Z. That is what you can see here. Z multiplied, all that is multiplied by beta, factor beta, and that is a factor beta. Okay, what happens if V is very close to small v close to V? That will be 1, that will be 1, that will be 0, B will be equal to infinity, so we are not getting any progress doing that, because you have infinity multiplied by a number, because the speed of electron inside the wire is almost at the speed of light, very close to B, and he is going to transform L, that's L is not going to be transformed, it's going to stay L, and he is going to transform the N, will be beta, N minus V over capital V multiplied by Y. As you can see, it's a very futile undertaking when you are assuming that the electron have to move very close to the speed of light inside the wire. So in that case, beta have to be equal to infinity. So what you accomplish with this equation, you accomplish almost nothing. Let us now follow the rationale of Einstein's application of relativity on the motion of electric charge in an electromagnetic field. The relativity principle demands that Maxwell-Hertz equations for empty space also be valid in the system K. K is a moving system. If they are valid in the system capital K. Another way, if you are applying Maxwell equations in the rest frame K, capital K, it has to be valid also in the frame that is moving with the electron, i.e. the vectors of the electric and the magnetic force, capital X prime, capital Y prime, capital Z prime, and capital L prime, and capital L prime, capital M prime, capital N prime, the magnetic forces of the moving system K, those electric and magnetic force, which are defined in this system by their bundle motive effects on the electric and magnetic masses or the electrons respectively satisfy the equations. Obviously, the two systems of equations, the two systems are the capital K and small k, or the rest frame and the moving frame, found for the system K must express exactly the same thing, since both are equivalent to the Maxwell-Hertz equations for the system capital K. Further, since the equations of the two systems coincide apart from the symbols representing the vectors, it follows that the functions occurring in the systems of equations at the corresponding places must coincide up to possibly v-dependent vector psi. Psi have to be v-dependent, which means depending on the velocity of the electron inside the coil or the conductor, which is common to all functions of one system of equation and is independent of the coordinates of on the system that is moving. The following relations will therefore be valid. We got these relations before, that this is a transformation function between the moving frame and the rest frame. In the case of x-axis, it was psi. In the case of beta-axis, how did he get this kind of transformation? I have no idea. He just made those up. He made this transformation in his own head. This transformation of the, most probably, he improvised them. The magnetic and the electric transformation between the frame at motion, the prime, and the frame at rest, that no prime. So he's going to determine the transformation function psi of v. If we now invert the system of equations, first by solving the equations just obtained, and second by applying the equations to the inverse transformation from small k to capital K, which is characterized by the velocity minus v, we obtain, if we take into account that the two systems of equations so obtained must be identical. We already obtained this kind of identity before, that proves that the transformation function have to be independent of the velocity. Whether you change it v or minus v, the product will be 1. We are indulged here in futile mathematics, proving that the transformation or the laws are valid, or a symmetry issue between the moving frame on the top of the electrons and the rest frame in the laboratory. Let us see the conclusion. Further, it follows for the reasons of symmetry that psi v equal psi minus v, of course it has to be equal to 1. And our equations take the form. That is being the rest frame, and that is being the moving frame. The moving frame is moving at the speed of light. So v is equal to 1, and beta is equal to infinity. So all that is nonsense. What is the footnote? E.g., x equal to y equal to z equal to l equal to m equal to 0. That's, for example, that's if, and n is not equal to 0, then it is clear n, which means the magnetic force, is not equal to 0. That is what he's trying to prove before, that if you have a magnetic force that is not equal to 0 and there is no electric forces, then it is clear for the reasons of symmetry that if v changes its sign without changing its numerical value, well, how are you going to have, here's the problem, you cannot have v if you don't have x, y, and z. If you only have magnetic field alone, the electrons are not going to move inside the conductor. So that makes no sense. By way of interpreting these equations, we shall add the following. Imagine a point-like quantity of electricity an electron whose magnitude measured in the system at rest K is 1 electron, for example, measured in the rest frame K, which when at rest in the system at rest exerts a force of 1 dyne on an equal quantity of electricity at a distance 1 centimeter. Suppose one electron at a distance 1 centimeter from another electron will exert a force of repulsion, this 1 centimeter. That force is 1 dyne. According to the principle of relativity, this electric mass is also of magnitude 1 if measured in the moving system, the small k. Well, how are you going to measure it in the moving system? Assuming that you are obsessed with symmetry. You are measuring it in the moving system. You have no way of measuring it in the moving system. If this quantity of electricity is at rest relative to the system at rest, the scatter k, the vector electric x capital X capital Y capital Z equals the force exerted on it by definition. That is if this quantity of electricity is at rest relative to the moving system, the small k, at least at the instant considered. The instant considered is what instant? The force exerted on it, on the charge, and measured in the moving system will equal the vector, the new vector in the frame small k of x prime, y prime, z prime. Hence, the first three of the above equations can be expressed in words in the following way. This is the way he is going to explain the transformation from one frame to another to reach a conclusion that does not make any sense, like many of the conclusions reached by Einstein don't belong to physics. Let us see the explanation. One explanation: if a point-like unit, electric charge, an electron, if a point-like unit, electric pole, is in motion in the electromagnetic field, like an electron moving inside a conductor, they will act on it in addition to the electric force. The electric force that is capital X, capital Y, capital Z. An electromotive force, that is the invention of Einstein. There will be an electromotive force, which, if we neglect terms multiplied by the second and the higher powers of V, ratio of V by speed of light, that electromotive force equals the vector product of the velocity of motion of the unit ball, which is a small v, and the magnetic force, which is capital M, capital N, capital L, divided by the velocity of light c, or capital V. That is the old mode of expression. The problem here is the velocity of the electron is huge, is very close to V, so that will make beta equal to infinity. Another way, if a point-like unit electric ball is in motion in an electromagnetic field, the force acting on it equals the electric force present at the location of the unit pole which is obtained by transforming the field to a coordinate system that is at rest relative to the unit electric pole. Another way, transforming the electric force from the capital K to small k. That is the new mode of expression. Analogous proposition apply for magnetomotive force. First he discusses here the electromotive force. Now he's applying the same on the magnetomotive force. Those are the second three equations. We can see that in the theory he developed his own theory. The electromotive force merely plays the role of an auxiliary concept whose introduction is due to the circumstance that the electric and the magnetic forces do not have an existence independent of the state of motion of the coordinate system. Another way, the electric force and the magnetic force do not exist unless there is motion of the coordinate systems. One of the systems belong to the conductor, the other belong to the magnet. In another way, the magnetic and the electric forces themselves have to move in order to come to existence. It is further clear that the asymmetry mentioned in the introduction when considering currents produced with the relative motion of magnets and the conductor, the asymmetry when he considers that moving a magnet relative to a conductor is not the same like moving a conductor relative to the magnet. A magnet will create magnetic field in the entire space. When the conductor moves, it only creates electric current inside the conductor. That asymmetry, he said, that asymmetry will now disappear. Question as to the seat or the origin of the electromotive force, unipolar machines also become pointless. Another way, he claims that he now was able to remedy the problem of asymmetry. There is no asymmetry anymore. We now turn to page 160, section 7, theory of Doppler's principle and aberration. Imagine in the system X, that is the system at rest, very far from the coordinate origin, a source of electromagnetic waves, which in part of a space containing the coordinate origin is represented with sufficient accuracy by the equations. So you have a source at infinity, almost at infinity, from the origin of the rest frame capital K. So the equations of the electric and magnetic fields will be the amplitude multiplied by a sinusoidal function. That sinusoidal function will have an argument of the angular frequency, the time, and the coordinate argument of the vector. V is the speed of light that we know it today as c. And the alpha, the A, B, and the X are the cosines, the direction cosines of the vector of the wave normal. And the X, Y, and Z are the coordinates of the frame capital K. That's the frame at rest, where X sub O, Y sub O, Z sub O, and L sub O, M sub O, N sub O are the vectors determining the amplitude of the wave train, and the A, B, and C are the direction cosines of the wave normals. We ask, what characterizes these waves when investigated by an observer who is at rest in the moving frame K? How are these waves be viewed in the moving system small k that is moving at a velocity small v? That's the velocity. Applying the transformation equation for electric and magnetic forces found in section 6 and those of coordinates and the time found in section 3, we obtain. Remember that those formula for the transformation of the electric and magnetic components, there is no proof for them. That is improvisation. That is Einstein just improvised. There is no proof at all for this kind of formulation. Multiplying by beta is also an improvised assumption. You cannot really prove it. He just assumed that if the target is, if the mass is moving, the magnetic force M will be modified by another factor, V over. We don't even know how he arrived to that conclusion. That term is completely hypothetical. There is no proof for it. There is no proof for that term, and there is no proof for multiplying beta in this transformation. And other assumption that we have before, that was the electron moving inside a conductor at a velocity v, that created this kind of transformation. But here you have another frame, an electron interacting with an approaching electromagnetic wave from a source at infinity. What we have here is the sinusoidal factor in all these equations. That sinusoidal factor that characterizes the wave when it is transformed to the moving frame of the electron will have, we understand that this part of the argument. But what we don't understand is how he reaches the conclusion that the angular frequency omega prime, he made another assumption without any proof that the omega prime equal to omega in the resting frame multiplied by beta, which is 1 over the square root of 1 minus small v over v squared minus the direction cosine in the x direction multiplied by the v, assuming v is in the x direction. How did he reach this formula? We don't know. I think he just makes it easy for himself. How did he get now the direction cosines in the moving frame? From the equations of omega prime, that is the transformed angular frequency in the small k frame that is moving, or the frequency of oscillation of electromagnetic waves as it is seen in the moving frame. Why is the frequency going to change, the angular frequency from one frame to another, assuming because of the linear velocity? From the equation for omega prime, it follows that if an observer moves with velocity v relative to an infinitely distant source of light of frequency mu, such that the connecting light source to observer, the line that connects the light source to the observer, that's along the, forms an angle phi with the observer's velocity, where the velocity is referred to in a coordinate system that is at rest, that is relative to the light source. Then mu prime, that is the frequency of the light perceived by the observer, that is the observer here is the electron that's moving at velocity v, is given by the equation. So the electron is going to see this frequency, while the light has this frequency, and the electron is moving with this angle toward the source of the light. This is the velocity of the electron, and this is the velocity of light, and that is the factor beta. If phi is 0, the term will be 1. If phi is 90, the term will be 0. Now, if the velocity changes each direction, the term is not going to change. The denominator is not going to change. But that term can be positive or negative, where if the velocity changes each direction, of course the cosine phi also is going to change its direction. So that term is going to be, the frequency will not be negative. This is the Doppler's principle of arbitrary velocity. For phi equals 0, the equation takes the simple form, that is the form if phi equals 0. Here, if the velocity is negative, if the velocity is 0, mu prime will equal to mu, which means that if the electron is not moving, it's going to see the same frequency. If the velocity is equal to v, you have a problem here, the frequency will be 0. The relative frequency will be 0, assuming there will be no frequency. If the velocity is negative, that will be double going the other direction, and that will be reduced. The frequency will increase enormously if it is going in the negative direction, or will be doubled. We see that contrary to usual conception, when v equal minus infinity, then mu equal infinity. I mean, when v is negative in the negative direction and increased very much, the frequency will be infinity. Does it make sense? It doesn't make sense at all. When you are a theoretician, you can make any assumption. If phi prime denotes the angle between the wave normal, the direction of the ray, in the moving frame, that's small k, the connecting line, light source observer, the equation for alpha prime takes the form, I think it is supposed to be phi prime. Phi prime equals, this equation expresses the law of aberration in its most general form. If phi equal pi over 2, pi over 2 means phi, that term will be 0, and that term will be 0. The equation takes the simple form, which is cosine phi prime equal minus v over v. It remains now to find the amplitude of the waves, the way it appears in the moving. Well, how big is the amplitude of the waves on the electron moving in a frame small k? If A and A prime denote the electric and magnetic force in the system at rest and in motion, so that will be at rest and that will be in motion. That will be or electric or magnetic. Respectively, we get A prime equals A prime square equal A square. We got that from previous assumption. We still don't have a very direct proof for it. That is the angle between the line of propagation of the electron and the light source. That is the velocity of the frame k of the electron, and that is the speed of light, and that is the amplitude of the wave in the resting frame, and that is the amplitude of the wave, the square of the amplitude in the moving frame, which for phi equals 0, if the angle equals 0, simplifies to this simple formula. It follows from the equations derived above that an observer approaching a light source with velocity v, v means the observer is moving at the speed of light. This source would appear to have infinite intensity, one of the hallucinations of Einstein. Well, why does it matter if the light source, if the observer moving at the speed of light toward another source of light coming to him, the amplitude will be infinite intensity? It means nothing whatsoever other than just a fantasy of the author.